So today we're going to talk about line integrals. So we're going to define an integral that's similar to a single integral. Now think about in the past what we have done. At that time we had this coordinate system. So this is this xy plane. And we're going to have an interval. Okay, at that time the interval is from A to B. Okay, so we have an interval over here. Okay, and then we have a continuous function over this interval. And then at that time, this function is called f of x. So y equal to f of x. Then we find the integral. And what do? We integrate this function. At this time, with respect to x. X go from A to B. And what does this integral correspond to geometrically? If this is a positive function, then this integral corresponds to the area under the curve, right? So that's the area under the curve when the function is a positive function.
Now think of this. Instead of integrating over this interval from A to B, over this line segment from A to B, we're going to integrate over a curve from this point A to this point B on the xy plane. Let's call this curve C. So here we have a function c equal to f of x and y. And when we integrate this function over this curve C, that is called a line integral. Although curve integral would be a better terminology.
The z coordinate is the function value. Okay, so every one on this line over here, we have a corresponding function value above. We're going to compute this line integral. We have this line integral of this function, and then over the curve.
Notice that before we integrate the function f on the interval a to b, we put dx at the end. That's because delta x was a small change on the interval a to b. Now we integrate the function over the curve c. The small change of this curve c is the differential of arc length, which we denoted by ds. So we put ds here at the end. ds is the differential of arc length. And then integrate over this curve c. Notice that if the function f is a positive function, integrating over the interval from a to b represent the area under the curve from a to b. Now if the function f of x comma y is a positive function, then this line integral over this curve c represents the area of one side of the fence or curtain in this figure.
This curve over here on this xy plane, we're going to parameterize it using a variable t. We can actually describe this curve here using parametric equations. Remember chapter 10 in Math 110b, right? We talk about parametric equation. Okay, so we express x here as a function of t and y as a function of t. So you can think about you driving a car, right? The curve here, y might not be a function of x. However, think about the t here as a time. At any given time, the x coordinate and the y coordinate are given. You cannot be at this x coordinate and another x coordinate at the same time, right? You cannot have two different x coordinates at the same time, okay? So x and y over here are function of t, okay? And the t over here go from a to b. So when t may be equal to a, the x will be here, right? And then the y will be here, and you get this point. And as t here increase from a to b, and then you trace out this curve. This curve over here, C, okay, so what is this? So this is the curve C, is given by this pair of parametric equation, x equal to xt, y equal to yt. Okay, this just means it's a function, the input is t, the output is x. Or equivalently, we can, by the vector equation, rt equal to xti plus ytj. Okay, so if you think about this r over here, okay, what is this r? So this r over here is remember is the vector from the origin point to a point, okay, on this curve. So imagine this is the r. Okay, I should use purple, I think. So let's use purple like this. Okay, so this is the r. Okay, that's the r.
Imagine that you have a laser pointer at the origin O, and that laser pointer, as the t here increase from A to B, is going to shoot the line starting from the starting point of this curve C, and then finally end up at the ending point of this curve C. R of t is a vector function. It has two component functions, one in the x direction, which is x of t, and the other one in the y direction, which is y of t. We assume that the curve C is a smooth curve, and this means that r prime is continuous, and r prime of t does not equal 0 when t goes from A to B.
Now let's recall from 10.2 the arc length formula. Okay, can someone tell me the arc length L? Well, I wrote it here. It's the integral of the differential arc length. So it's the integral of the differential arc length. For the differential arc length, do you guys remember what did we put over here? For those people who took Math 110B, I hope you remember. ds equal to was if I put the dt outside, because this is dt, right? So because this is dt over here, okay, then this is dx dt. Okay, good. It is dx dt square plus dy dt square. Okay, remember. Okay, let me refresh your memory. So remember for ds. Okay, if y here is a function of x, then ds is equal to, you represent this as the square root of 1 plus dy dx square dx. This is given when y is a function of x. So you put dy dx over here, right? Okay. And if x here is a function of y, then what is ds? You can remember? Square root of, then this time we put the dy outside. And what should I put over here? 1 plus. This time will be dx dy. Okay? Differentiate x with respect to y. So dx dy square, okay, like that. And this is for x and y function, okay, when they are function on each other, like that. Okay? And when it's parametric equation, when you given this one over here, x is a function of t, y is a function of t, then ds over here is going to be equal to, this time we're going to put the dt outside, okay, and then we're going to put dx dt square plus dy dt square. Depends on what kind of curve you get. So if this is a parametric curve, okay, x and y are function of t, the differential arc length will have the dt outside, and then dx dt square plus dy dt square under the square over here. So go back to this. So this is how we got that. So t go from A to B.
So here is the formula to evaluate the line integral.
Now this line integral of this function over this curve C, remember, imagine that curve. Okay, let me give you the picture. C is this curve over here. Okay, this curve over here. And you use the function. What's the function? Okay, let me write the function over here. This is f of x comma y. Okay, z equal to this, right? This function over here, when you integrate this function over this curve C on the xy plane, so what will be the formula? Okay, let's discover this together. So first of all, I'm going to express this ds over here. Remember, that's the differential arc length, right?
Because x and y are being parameterized by t, so we express ds, the differential arc length, as the square root of the sum of dx dt square and dy dt square, and then leaving the dt outside the square root.
Now what about this function here? This is an integral with respect to t. We want everything here to be in terms of t, right? So x here is equal to, remember x was expressed as a function of t, so that's xt. Y is the function of t, so that's yt. So you express x and y in terms of t, and now you get the formula. Got it? Maybe some example after this. Okay, so the idea here is to express everything in terms of this parameter t. Okay, maybe I should color code this parameter t. This parameter t over here, you want to express everything in terms of it. And you use the parametric equation to express this x and y. Okay, we replace x and y by those function of t. So this one here, it was what we talked about in the beginning of the lecture. For the one-dimensional case, when you integrate this function over an interval from a to b, this one here is just a special case of the line integral when you have this line over here on the x-axis. So it's the same formula we have. This one here corresponds to the area under the curve when this is a positive function. And when this function that we do line integral with, it is a positive function, and that corresponds to the area of one side of the fence or one side of the curtain. Let's try one example. We're trying to evaluate this line integral where C is the upper half of the unit circle. So here's a picture. This is the unit circle, but we only get the upper half. We're going to integrate this function over this curve on the xy plane. So first of all, in order to use the formula we had before, we had to first find the parametric equation for x and y in terms of t. Okay. Now in this case, this is the unit circle. I'm going to let t to be the center angle. So I'm going to let this to be t. The t here stands for the center angle. So what does x equal to? Anyone tell me? Okay, so r cosine theta, but what is r for unit circle? So that will be just cosine of t, because r is 1, so that will be just cosine of t. So cosine t, that's the x coordinate of this one, right? Okay, so I can write it down, cosine of t, and this is sine of t, right? So cosine t, sine of t, okay? So we found the two parametric equation in terms of t. Now t go from what to what? T go from 0, right? The smallest t is 0, and then all the way to pi. The t go from 0 to pi. So we got this one right here. Now once you found this, then we should be able to do this. So what are the steps? First of all, I'm going to ask you for the ds over here. Do you guys remember what should I put over here? dx dt. Okay, dx dt and dy dt here. dx dt here and dy dt here, right? And what should I do with this function? This is an integral with respect to t, so you want to express them in terms of t. What do we do to this? So you have 2 plus, we replace the x here by what? Cosine of t, right? Yeah, thank you. Okay, so the x over here is cosine of t, the y here is sine of t, so you just replace them, okay, express them in terms of the parameter t, right? So you got that. Okay, good job. Now after that, we're going to find dx dt and dy dt. So what is dx dt? X is this, dx dt is negative sine t, right? Yeah, you got it. And then dy dt is cosine t. When you square that, that will become sine square t plus cosine square t, which is equal to 1, right? So then this integral will be, and then we find antiderivative of 2 is 2t, antiderivative this is this. What kind of method I use to find antiderivative here? Do you guys remember from Math 110b?
Yes, u sub.
And that u equal to cosine t. You should get this. All right, so just do the calculation and that will be the result. What does this one here correspond to? You can think about that is the area of one side of the fence of this function over this curve, over this half unit circle right here. And imagine that above this half unit circle on the xy plane, and you have a fence. And the function value, the height of the fence is going to be given by this function. And the area of the fence, one side of the fence, is going to be equal to this. Before we talk about that formula applied to curve that is smooth curve, right? Now, if the curve is not smooth, but it's piecewise smooth, okay, like this one. It is smooth over here, smooth here, and here, and here. So if you chop it into individual pieces, each pieces will be smooth. Then this curve here is called a piecewise smooth curve. So it is a union of a finite number of smooth curve. We can divide the line integral of this function over that piecewise smooth curve by separate that into integral over each smooth curve and then sum them up. So imagine you're building up a fence, right? So over this curve, you have a fence, and then over here, a fence. And then if you try to find the area of one side of the fence, you can add that the area over this, area over this, and this, area of the fence. And I put the formula here so you can refer to, but after a while, you should be able to do it without looking at the formula. This time, we're going to evaluate this function 2x over this curve C. So this curve C, okay, let's highlight this, consists of two pieces. The first piece is going to be from here to here. That's the first piece right here. This is C1. And then the second piece, I'm going to use a different color. It's going to go from here to here.
Since both C1 and C2 are smooth, C is a piecewise smooth curve.
Well, just consider that piece by piece, right? So let's integrate this. Let's integrate this over the first piece, which is C1. And then later on, integrate that over the second piece, which is C2. And then we sum them up, right? So imagine you build a fence over this, a fence over this. Then you can add up the area of the fence later, right? Okay, but when you do this, the first thing to do here is you need to find the parametric equation of this piece over here in terms of a variable. Now, you will say, what parameter should I use? Looking at this one over here, it is, well, they were given you, right? This is y equal to x squared. So this one here is y equal to x squared. And you see that y here is a function of x, right? So the lateral choice to parameterize this curve over here is let x here to be the parameter. That way, because for every point on this curve, okay, let's think about it. For every point on this curve, the first coordinate is x. The second coordinate will be x squared. So x is equal to x, and then y is equal to x squared. The parameter we use for this piece over here is x. So x equal to x, y equal to x squared, and x here go from 0 to 1. So this will be for C1. Okay, now once you have this, just like before, we try to first, remember we try to figure out the ds over here, right? ds will be dx dt square plus dy dt square, square root, and here dt. But this time we're going to have an x. So what should I have? Okay. In this case, for C1. For C1 over here, dx is equal to square root of, at this time the parameter over here it is dx, right? The t here is the same as x, okay? And remember, x is equal to x, y is equal to x squared, and x is going to greater than equal to 0, less than equal to 1, right? So the parameter over here, if I use the green color for the parameter, okay, the parameter we have over here is the x. So x is the parameter. So this is dx over here. And what should I put inside? Inside here it is dx d what? dx. Yeah, the parameter is x, right? Okay, so this is t. This is t. So at this time, t is x. So dx dx. So then square and then plus this one here is dy dx and then square this, right? So for C1, the x is a parameter. So you have this. So this is exactly what we have here. Yeah, dx dx, okay, and then dy dx squared. And the parameter over here is x. Okay, and then what about the 2x over here? Do I need to change? Do I need to change to other variable? Well, remember, has to be in terms of the parameter, right? Is it in terms of the parameter x already? Right? So the 2x over here, you don't need to change it. So this 2x over here is already in terms of x. All you have to do is just copy it down. Okay, so it is 2x. It's the same thing. Or this is already in terms of x, in terms of the parameter. So nothing need to be changed. Okay, so just copy that. And then you see the x here, x go from 0 to 1. So you have this. Then after that, you can just evaluate this integral. What integration method you think you're going to use over here? Use up, yes, use up, okay? So you will use up and you let u to be 1 plus 4x squared. Okay, good job, okay. So this one here, we're going to let this be u, okay? So we're going to do use up, okay, like that, okay. And then by using use up, you should be able to get this result, okay? Okay, good. So that was for C1. Okay, now let's look at C2. The C2 will go from here to here, right? Okay. This one here, we can express this. X is equal to 1, and Y is, well, let's look at the X and Y coordinate of this, right? Okay. So for every point here, they have the same X coordinate, which is 1. And then the Y coordinate vary, right? So every point over here, X coordinate is 1, Y change from 1 to 2. So we have this pair of parametric equation right here. So literally, the parameter here will be the y, okay? Y is a parameter. So y is in place of the t, in this case, for this piece of curve. Now when we do that, then we have this dy over here. Now what should I put in this first parenthesis over here for the ds? For this is the ds, right? What should I put in the first parenthesis? This, before it was dx dt, so this one here will be dx dy. Yeah, you got it. And then the second one will be dy dy, right? Okay. Dy dy is just 1, okay? And dx dy is going to be 0, okay? So then you get 1 for this one, okay? What about the 2x? Do I need to change it? Well, it had to express in terms of this parameter y, right? So what do we have for x? X is what? 1. So this is just 2. Okay, x is equal to 1. So this is just x is 1. So this is just 2. So we should have a 2 over here. Okay, now we settle the integral and then evaluate that, we get 2. So finally, that integral over the union of these two pieces will be the sum of the two integral, and that's the result. So that's how we do piecewise smooth curve, an integral. You see, you got it? Okay. All right. Think about the area of one side of the fence. Okay. So you build a fence along this on the ground, and then sometimes the fence go up and down, up and down. Okay. And then like this is the area of the fence. Okay, the physical interpretation, like integral, depends on the physical interpretation of the function. Remember, mass of the subject. So if rho here represent the linear density, okay, think about here. Think about here as a wire. Okay, a wire over here. You have a wire over here is in this half circle shape. And then the rho over here is the linear density. So what does the linear density mean? Linear density means for each unit length, the density of each unit length over there. The mass of this y over here is the integral of this linear density over this curve. If you want to calculate the mass of the wire, you will integrate the linear density over this curve. Okay, so imagine this is y. So the first example we went over, we have this function, right? The function we have is this. So imagine that this is linear density function. Then the result that we got before will represent the mass of this y over here. So every time you try to get the mass of some thin wire or some other object, you can use the integral of the linear density over that curve. Okay, the next one. This one here talk about center of mass. This is the formula. Remember, x bar over here is the x coordinate of the center of mass, and the y bar here is the y coordinate of the center mass. And these two are the formula, and you can use it for your homework. Now this time again we have a semicircle like this, and it's a wire. But this wire over here is going to be thicker near the base. Let me exaggerate this a little bit. Down here is thicker, and then up there should be thinner. So kind of like an arch over here. Now it says that the linear density at any point is proportional to its distance from the line y equal to 1. So the line y equal to 1 is this line over here. Then it says the linear density is proportional to distance from the point to this line. Okay, let's just pick a point, okay, a sample point. Let's take this point over here. Label this x comma y. The distance from this point to this line, what's the distance from this point to this line? The top subtract the bottom, right? The top is what? 1. The bottom here is what? Y. So the distance from this point to this line is 1 subtracting 1, right? So 1 subtracting y, the top subtracting the bottom, right? That distance there is 1 subtracting y. Okay, that's the distance. Okay, and it says that the linear density is proportional to this distance. So you just use k multiplied by this distance, 1 minus y, right? That's the linear density function in terms of y, where k is a constant. Now we calculate the mass of this y over here. Remember, to calculate the mass, we use the integral, the line integral of this linear density, right? Remember, this one here is a rho, right? And integrate over this curve over here. So ds over here, and then c over here. So c is this one right here, okay? And this is 1 minus y. Now, for the ds over here, how do you figure out this dsm? So what will be this ds over here? Once you think about, you have to express x and y in terms of their parameter, right? So this is the half a unit circle. So just like before, the parameter you use will be what? Will that be the center angle t, right? Okay, you can let x to be cosine t, y equal to sine t, t go from 0 to pi, just like before. Then by doing that, we parameterize this curve using the t. T corresponds to the center angle. So we have this. Now from this, what does ds equal to? Okay, let's just do it. They say it's equal to dt, but let's do the calculation. So ds is square root of dx dt square plus dy dt square. What's dx dt here? Negative, okay, good, negative sine t square, okay, cosine t square, okay, dt.
But this part here will sum up to 1 by the trig identity. So ds is equal to dt.
Now, you can just replace the dx here by dt because of this one right here. And then you just do the calculation of phi antiduality, and then you should get this result. What does this result here stand for? It stands for the mass of this y over here, with the linear density being defined as this, okay, proportional to the distance from this horizontal line over here. Okay, so this is the mass of this y over here. Okay, now, and then you can calculate the center mass, okay, using the formula above. So you can calculate the y-coordinate center mass using the formula that were given, and you get this. The x-coordinate of the center mass because of the symmetry, right? So this side and this side are symmetric. So the x-coordinate of the center mass has to be 0. So therefore, the center mass is actually here. So this piece of y over here with that linear density, it has the center mass here.